It is a dark and stormy night. But let's film anyway. Hi everyone, welcome back to Cody'sLab. So recently a fan over on Reddit asked me to explain a phenomenon that they had stumbled across. And this was actually something that I had done in a video many years ago. Unfortunately, back when I was filming with a potato. I mean, I'm not filming much better now, but the overexposure is not the camera's fault. Assuming that I can do a little bit higher quality video, let's redo it, shall we? So this here is a very strong 3-inch diameter neodymium magnet. It's not necessary to be this strong, but it does help for this demonstration. So now I'll take some iron nuts. You can see here, this is what you would screw onto a bolt. They're just ordinary nuts, mostly iron, a little bit of carbon, steel. If I bring them over close to the magnet, you can see that they begin to stick together, which they weren't doing earlier. In fact, I can form long chains out of them. See that? But what is really interesting is that I can actually lift them up off the magnet. And the magnet, as strong as it is, see, will not pull the nuts from the other nuts. See that? I can just stick them right together. But you can see that when I bring them away from the big magnet, they stop being attracted to each other. Now this works with all ferromagnetic materials. So I got some steel ball bearings here. Those can form the chains. I got some iron rings. This is actually what I used in the first video. You see, they can do it too. In fact, you can kind of follow the magnetic field with them. And you can even do it with something that is not iron, such as this nickel strip here. This is a piece of nickel, and of course it does the same thing. So what's going on? Well, the short answer is that ferromagnetic materials copy the magnetic field that they are placed in. So basically, a piece of iron, when placed next to a magnet, becomes a magnet. So I can kind of explain this by taking a bunch of magnets here. They're all jumbled up. This is kind of what the structure of a chunk of iron, nickel, or cobalt looks like. But when you place it in a magnetic field, okay, this is going to be rather dangerous, but let's see if I can do it anyway. They change their orientation. See that? All those little pieces of magnet have now flipped and they're all lined up. And when that happens, this is now one big magnet. Iron does the same thing. It's just on an almost atomic scale. But the difference between a piece of steel and the little magnets here is that when I take it back away from the magnetic field, these stay oriented, but a piece of iron will kind of self-scramble. All those magnetic field domains which lined up in the magnetic field and brought away should scramble themselves again. It does depend on the alloy and the material that you're working with. In fact, these iron rings here, which I used in the first video, if I stack these together, bring them in real close, good strong magnetic field, so now all those magnetic domains are kind of lined up. Now I'll slowly pull the big magnet away. Just try not to shake them around too much. Just take that far away. You can see for a while the rings were able to stick together without the magnet influencing them. And that's because those domains actually stayed lined up for a little while. Some materials do it better than iron, such as this piece of ferrite. That's why this is actually a permanent magnet. So if I bring this next to the big magnet, hang on, I gotta go let the cat in. So if I bring it next to this strong magnet, you can see in this orientation it attracts. But if I flip the big magnet around, then the little magnet doesn't want to line up with it, opposite. The little magnet does the little magnet does not want to go to this big magnet, because now the poles are opposing and opposite poles repel. But if I force it down, eventually it'll stick. And what has happened here is now all those magnetic domains have flipped and reoriented with this big magnet. And now when I pull it away, it doesn't flip anymore. In fact, it's attracted. If I flip the big magnet over again, you can see now the little magnet wants to flip again. But if I force it down, it remagnetizes it, and it remembers that magnetism and doesn't want to stick the other way. So now you should be able to understand why these pieces of iron stick together. They have become magnets, and they're always going to be oriented north-south, north-south. Unless, of course, you turn them sideways relative to the original magnetic field, in which case they actually repel each other. You see, it's kind of like these two permanent magnets here. If you take them, they're attracted together, so south end, north end. But if I pull them apart, flip them like this, so that the two north ends are facing up, and I bring them together, they repel. That's because the two north ends really want to be as far away from each other as possible, and so one of the magnets will want to flip over before they'll actually stick side by side even. And of course the same thing's happening with the pieces of iron. The magnetic field is going down towards this big magnet, so turning them sideways will cause their magnetic fields to be oriented, both north up, and that causes them to want to repel. In fact, you can really see this quite well if I take a couple of ball bearings and put them in my palm and then lower them onto the big magnet. The bearings will actually force each other apart. So let's try one more quick experiment. I have an oxyacetylene torch here. So let's turn this on. Turn on the oxygen. So now what I'm going to do is I'm going to heat up one of the balls in this chain till it's past what is known as the Curie point. The temperature at which the random thermal perturbations are so strong that the magnetic domains are kicked around so much that they can no longer align to a magnetic field. Basically, the metal stops becoming a magnet and will just fall right off. And now I'm burning my table. So now that I've explained how the pieces of iron become magnets when placed in the magnetic field, I can finally answer the original question. These pieces of iron are not stolen away from each other by the larger magnet because they have their own magnetic field, which is adding to the magnetic field that is being generated by this magnet. It kind of has the effect of making the magnetic flux travel through the iron much more efficiently than it does through the air. In the air, the magnetic field strength decreases with the inverse square, the same as light and gravity does. So if you get 3 times as far, the magnetic field is 1/9 as strong. But if it's going through iron, or a ferromagnetic material, this is not the case. So what this means is that if I take a piece of iron and hold it above the magnet about the same height as the top of these pieces of iron, it's pulling down, quite strongly, but I can easily hold it up. It's not that strong. But if I move it so that the iron here is directly underneath, the attraction becomes substantially stronger. But it's not just the stack of iron pulling down. This piece of iron is pulling up, equal and opposite forces. This makes them stick together with about twice the amount of force that the large magnet is pulling down with. That means that I can actually pull the entire stack of iron right off the magnet. This does have limits, of course. It's not exactly double. If I move them over to the side here, the magnetic field on the edge of this magnet is quite strong. It's very concentrated right here, and so it can actually pull the stack apart if I focus it right into that area, but it can't do it with just a couple of magnets. It can't do it with just a couple of nuts here. See, I'm still able to pull it off as long as the stack is fairly short, as you can see. I'm kidding. So hopefully this clears some things up. Hope you enjoyed. I'll see you next time.